Hello, my name is Yanai. I'm a graduate student from Department of Artificial Intelligence from Itrc University. Currently, I am conducting my research at the WISE Lab under the supervision of my professor, Sanyun Oh. So today I will make the presentation for the switch migration-based log adaptation mechanisms in distributed SDN control plane, which I was presented this presentation in the August 2020 in Hangul Tongshin Hardware Conference. So this is the outline of my presentation. So firstly, I will introduce the topic and then I will present the motivation of my research topic. After that, I'm gonna present the recent work related to my topic and then I will move to the discussion session of my findings. So the final session of this presentation is concluded with the discussion and the conclusion session. So the first session is introduction. So currently, the growth of data traffic and ever-increasing use of mobile devices in modern internet basically challenge the conventional internet architectures. Figure 1 shows the architecture of conventional networking. In here, control logics are embedded inside the networking devices. Therefore, traditional networking infrastructure requires manual configuration changes to adjust the particular networking policy. On the other hand, such manual modification impacts the required quality of service or quality of experience. The new paradigm in networking, which is called software-defined networking or the SDN, offer the programmability to the network by decoupling the control logics from the networking device. As shown in the figure 2, the SDN architecture is composed of set of switch and the centralized controller. So the packet message is sent from the switch to the controller to install the control rules when the new flows arrive. The control plane can be single or distributed with logically centralized manner. The physically distributed with the logically centralized control plane design is used to address the scalability and reliability issues of the single controller design. So although the distributed controller address the scalability and reliability issue, network traffic vary with time and speed, and the distributed controller with the static configuration limit the capability of the controller load adaptation in dynamic environment. Furthermore, a controller may become overloaded when the switch mapped to this controller suddenly observes many flow, while other controllers remain underutilized. There are alternatives to address the load adaptation issue in dynamic controller design. One way is over-provisioning the controllers, but it is a costly solution. Another alternative is switch migration. In switch migration, dynamic switch to controller mapping with well-defined design is needed in order to fully utilize the available resources. So, despite load balancing, switch migration-based mechanism raises many challenges, including cascaded load imbalance and suboptimal load balancing issues. In this paper, we first review the previous switch migration techniques, and then we will discuss the two main phases of the switch migration that we need to consider in constructing robust switch migration-based load adaptation mechanisms. So the next session is the review of the recent work related to switch migration-based load adaptation techniques. So the first work is done by Jean and co-authors. They address the issues of static configuration of switch to controller mapping with the dynamic decision making based on the response time delay of the controller packet and processing latency. However, the delay of response time is directly proportional to the link state and network condition. Another effort done by Chen and co-author is that switch migration technique with random selection of switches from overloaded controller when an even load distribution is detected. In their approach, random selection of switch might lead to new load imbalance after migration. On the other side, Wan and his affiliated authors proposed the multiple controllers load balancing with migration efficiency model. Nevertheless, it might provide suboptimal load balancing performance because their model compares every switch from overloaded controller domain with the newly selected controller to maximize migration efficiency. So the comparison time might impact the load balancing latency if the network size is large. Other recent approach is done by Zhu and co-author is that they propose switch group migration for the load balancing. Their approach increased migration costs because of the extra unnecessary migration of switches. Their purpose is to maximize the network utilization and the switch group with total bandwidth less than the average network capacity is selected to migrate from overloaded controllers to the underloaded one. So in the recent version of the OpenFlow protocol, they also propose that each switch can be controlled by the multiple controllers. However, there is no suggestion for the specific mechanism or switch migration or the controller rule changes in the protocol. Therefore, existing switch migration techniques construct their own design with different consideration for load imbalance detection and switch migration process. So in here, we will discuss the two phases of switch migration: monitoring phase, which monitor the load imbalance data of the control plane, and the load adaptation phase. This phase decides which switch to be migrated to which controller. So the next slide is the findings of the monitoring phase. So in the monitoring phase of existing approach, they detect the packet frequency to measure the controller load. Since the control plane is physically distributed, as shown in Figure 3, communication between controllers with the east or westbound API is performed to grant the strong consistency of global controller view. So this load may vary with the switch migration happening in today's dynamic environment. So moreover, the freshness of data is also important in switch migration load adaptation decision process. Most of the existing switch migration mechanisms use the data from default controller storage, for example, flow-like controller, which provide the snapshot statistic by default. Another popular controller in the industry is OpenDaylight ODR, which provide the distributed data store architecture, which store the monitor data into shard and cluster member maintains a subset of shard. To access the global control plane view, shards in the ODR must synchronize each other, along with the east and west communication will increase. One way to granny the freshness of data is directly monitor the data from OpenFlow counters, which we can take the advantage of the counter statistic by the OpenFlow enabled devices. However, the frequent collection of data might impact the southbound network traffic or the SDN network between the controls and the data plane. Therefore, comprehensive distributed control plane load measurement with the fine-grained monitoring is necessary in building efficient switch migration techniques. So the next phase is the analysis for the load adaptation phase. So the load adaptation phase starts with the deciding which switch should be migrated to which controller. Most of the existing switch migration techniques select the heavy switch from the overloaded controller and directly ship the switch to the underloaded controller. So this can happen the cascaded load imbalance. As shown in Figure 4, there are three controllers with the associated load. With the controller threshold for the load imbalance is 90% of the total controller load. As shown in the figure, controller 1 has the total load of 85%, which is composed with switch 1 and switch 2 load, which is almost overutilized. So when the controller 1 decides to migrate the switch, it will select that switch 1 as the candidate for the migration. So the underutilized controller will be the controller 3. So if we directly migrate the switch 1 from controller 1 to controller 3, the controller 3 load imbalance threshold will directly happen. So this kind of imbalance is called cascaded load imbalance. So to avoid this kind of problem, we can consider more types of mode, but this can lead to long load balancing time. Instead of directly shipping the switch to interload the controller, we can make some kind of swapping the switch between the controllers. It can also address the cascaded load imbalance problem, but we have to consider with the time latency of load balancing decision making. If it is take long time, which can cause the suboptimal load balancing performance. So therefore, optimal switch to controller mapping with dynamic migration is also important in designing robust switch migration based load adaptation technique. As for the conclusion, we found out that the careful consideration of monitoring data and migration mechanism is needed in the design of efficient switch migration mechanism. Our study focused on the two phases of existing switch migration-based load balancing mechanism in the control plane. We also made thorough discussion for these two phases in order to get useful insight in designing switch migration-based load adaptation mechanism. With the consideration in mind, we intend to explore the efficient switch migration-based dynamic load adaptation technique as part of our future work. Thanks for paying attention for my presentation.